Somewhere in a lab in Santa Barbara, a chip the size of your thumbnail just did something that should be impossible. It solved a problem in under 5 minutes. The same problem, given to one of the fastest supercomputers on Earth, would take 10 septillion years. Write that number out, and it's A1 followed by 25 zeros. The universe itself is only about 14 billion years old. So this chip didn't just beat a supercomputer, it beat the age of the universe by a factor so large that human language barely has a word for it. But here's the part that should actually worry you, or excite you, depending on which side of this you're on. That headline number isn't even the real story. The real story is buried in a problem that physicists have been quietly terrified of for almost 30 years. A problem that, until now, nobody could prove was actually solvable. Google says they just solved it. It's called Willow. And by the end of this video, you'll understand exactly why some scientists are calling it the most important hardware result in the history of quantum computing, and why others are telling you to slow down and not believe the hype just yet. Let's get into it. Segment 1. The 30-year problem. Nobody could crack to understand why Willow matters. You have to understand the one thing that has been quietly killing quantum computing since the very beginning: errors. Here's the thing about quantum bits, or qubits. A regular computer bit is rock solid. It's a 0 or a 1, full stop. You could throw your laptop down a flight of stairs and most of those bits would still hold their value. Qubits are the opposite of that. They're built from things like superconducting circuits, cooled to temperatures colder than deep space, and they are absurdly fragile. A stray vibration, a tiny fluctuation in temperature, even cosmic rays passing through the chip, any of it can corrupt the information stored inside. Qubits don't just store a 0 or a 1, they store a delicate quantum superposition of both. And that superposition collapses if you so much as look at it wrong. So almost as soon as quantum computing was theorized, scientists hit a wall. If you want a quantum computer powerful enough to actually do something useful, crack an encryption key, simulate a new drug molecule, design a better battery, you need a huge number of qubits working together. But the more qubits you add, the more chances there are for something to go wrong. It's like trying to build a card tower in a windstorm. The bigger you build it, the more it collapses. In 1995, a mathematician named Peter Shor proposed a way out: quantum error correction. The idea was to take a bunch of noisy physical qubits and bundle them together into a single, more reliable logical qubit, essentially using redundancy to protect the information, similar to how you might write down an important phone number on 3 separate pieces of paper in case you lose one. It's an elegant idea on paper, but for nearly 3 decades, nobody could actually pull it off in practice. Every time researchers added more physical qubits to try to make a logical qubit more reliable, the system actually got worse, not better. More qubits meant more noise, more chances for error, more chaos. Scientists called this being above threshold, meaning you'd crossed into a zone where scaling up made things worse, the exact opposite of what you needed. Proving you could go the other way, that adding more qubits could make errors go down, became one of the most sought-after milestones in the entire field. It's called crossing below threshold, and for 30 years, it stayed just out of reach. Until December 2024, when Google says they got there. Segment 2. Meet Willow. Willow is Google's newest quantum processor, built at the company's own chip fabrication facility in Santa Barbara, California. It's the successor to Sycamore, the chip Google used back in 2019 to make its first big quantum supremacy claim, a claim that, as we'll get to later, didn't exactly hold up cleanly. On the surface, Willow looks like an upgrade in the usual sense. It packs 105 superconducting qubits onto the chip, roughly double what Sycamore had. Its qubits can hold information, what physicists call coherence time, for around 100 microseconds, which is about 5 times longer than its predecessor managed. That might sound like a tiny sliver of time, and it is, but in the world of quantum hardware, that's the difference between a computation that actually finishes and one that dissolves into noise halfway through. But the qubit count and the coherence time aren't really why people are losing their minds over Willow. Those are incremental expected improvements, the kind of thing you'd predict from any new generation of hardware. The headline isn't the spec sheet. It's the experiment Google ran to test something much deeper. Can a quantum computer actually get more reliable as it gets bigger? Segment 3. The experiment that broke the 30-year wall. Here's what Google's team actually did. And it's worth slowing down for because it's genuinely elegant. They took Willow's physical qubits and grouped them into grids using a method called the surface code, essentially arranging qubits in a checkerboard pattern where neighboring qubits constantly check each other for errors, a bit like a group of proofreaders all cross-checking the same sentence. They started small, a 3x3 grid of encoded qubits. Then they scaled it up to a 5x5 grid, then again to a 7x7 grid. Each time they made the grid bigger, they were adding more physical qubits into the system, exactly the move that, for 30 years, had always made error rates worse. Except this time, it didn't. Each time the team scaled up the grid, the error rate was cut roughly in half. 3 by 3 to 5 by 5, the errors dropped. 5 by 5 to 7 by 7, they dropped again by about the same proportion. That pattern, error rates shrinking by a consistent factor every time you scale up, is what scientists mean by an exponential reduction. Or worse, it is, in plain terms, proof that you can build a bigger quantum system and have it become more trustworthy, not less. This is the result Google published in the journal Nature in December 2024, and it's the part of the story that quantum physicists actually care about. Hartmut Neven, who leads Google's quantum AI division, called it the most convincing prototype yet built for a scalable logical qubit. That's a careful, deliberate phrase. Prototype, not solution. But even as a prototype, it represents the first hard evidence that the entire theoretical foundation of fault-tolerant quantum computing, the foundation Peter Shor proposed back in 1995, actually works the way the math said it should. For 3 decades, that was an open question. Willow is the first chip to give it a real, scientifically verified, peer-reviewed answer. Segment 4, 10 septillion years, and the ghost of Sycamore. Now let's talk about the number that actually went viral. The 5-minute computation that would supposedly take a classical supercomputer 10 septillion years. The benchmark Google used is called random circuit sampling. Without getting too deep into the math, think of it as an extremely elaborate, deliberately chaotic dice game that's almost perfectly suited to how quantum mechanics naturally behaves, and almost perfectly unsuited to how classical computers calculate. Google ran this benchmark on Willow and clocked it at under 5 minutes. They then estimated how long it would take Frontier, one of the most powerful supercomputers currently operating, capable of more than a quintillion calculations per second, to do the exact same task using the best-known classical methods. Their estimate? 10 septillion years. That's a 10 followed by 24 zeros. It's a staggering number, and it's the kind of thing that makes for an unbeatable headline. But if you've followed quantum computing for a while, you might be feeling a sense of déjà vu right now, and you'd be right to. In 2019, Google made an almost identical claim with Sycamore. They said it completed a task in about 200 seconds that would take the Summit supercomputer roughly 10,000 years. It was front-page news around the world. The phrase quantum supremacy entered the public vocabulary. Then classical computer scientists got to work. Within a few years, researchers found smarter, more optimized ways to simulate that exact same task on traditional hardware. And the 10,000-year estimate quietly collapsed down to a matter of days, then potentially even less. The supremacy claim wasn't fabricated, but it wasn't permanent either. It was a snapshot of a specific moment in a race between quantum hardware and classical algorithm cleverness, and classical software clawed a lot of that gap back. Google is aware of this history, and to their credit, they've addressed it directly. Neven has said the company fully expects classical computers to keep chipping away at these benchmark numbers, just as they did after 2019. The argument Google makes now is a more nuanced one. Even if classical algorithms improve, the gap between quantum and classical performance grows at what they describe as a double exponential rate as you keep scaling the quantum side up. In other words, classical computers might claw back some ground, but quantum hardware should keep pulling further and further ahead over time, not converge back toward parity. It's a more careful claim than 2019's. Whether it survives contact with 3 more years of classical algorithm research is, honestly, still an open question. Segment 5. The skeptics have entered the chat. If you only watched Google's own announcement video, you'd walk away thinking quantum computing had basically been solved. That's not quite where independent experts in the field land. The most common pushback is about how good below threshold actually needs to be before it's useful. Willow's logical error rate, the rate at which its protected bundled qubits still mess up, sits at roughly 0, 14% per cycle. That's a real improvement and a real scientific milestone. But most researchers believe you need error rates closer to 1 in a million, not 1 in 1,000, before you can run the kind of large, deep, multi-step algorithms that would actually crack encryption or simulate a complex molecule. Willow's result proves the trend line is going the right direction. It doesn't mean the destination has been reached. There's a second, more technical caveat. What Willow demonstrated below threshold for was preserving a logical qubit in memory, essentially keeping stored information stable and intact over time. It has not yet demonstrated below threshold performance for logical gate operations, the actual computational steps you'd need to chain together to run a real algorithm. Protecting a parked qubit and reliably computing with one are related problems, but they're not the same problem, and the second one is harder. And finally, there's the obvious point. As of right now, nobody, not Google, not anyone else, has run a quantum computer to solve a real-world commercial problem that classical computers couldn't already handle. Every headline-grabbing benchmark so far, including Willow's, has been a deliberately constructed task designed to favor quantum hardware, not a practical use case like drug discovery or logistics optimization. Google has said openly that this is the next frontier they're chasing, not something they've already achieved. None of this means Willow isn't a big deal. It means the honest version of the story sits somewhere between quantum computing is basically solved and this is all hype. And that honest middle ground is still genuinely remarkable. Segment 6. The follow-up that made skeptics pay attention. Here's where the story gets more interesting, because Google didn't stop at the December 2024 announcement. In October 2025, Google's quantum team announced something they called quantum echoes, running on the Willow hardware. This time, the framing was different and arguably more important. Google described it as the first verifiable quantum advantage achieved on real hardware. The verifiable part matters enormously here, because it directly answers the criticism that hit Sycamore back in 2019, that the original result couldn't be independently checked using classical methods, which is part of why classical researchers were eventually able to chip away at it. Quantum Echoes was reported to run roughly 13,000 times faster than the world's fastest supercomputers on its target task, and crucially, the result could be cross-checked and verified rather than just estimated. It's a smaller, more specific claim than the headline-grabbing 10 septillion years benchmark, but in some ways, it's the more scientifically meaningful one, because it's built to withstand exactly the kind of scrutiny that eroded the 2019 supremacy claim. This is the pattern worth watching with Willow going forward. Less about chasing the single biggest, flashiest number, and more about building results that can survive peer review, independent verification, and a few years of classical computer scientists trying to prove you wrong. Segment 7. What this could actually unlock. So let's say the trend line holds. Let's say error rates keep dropping as Google scales Willow's architecture up toward the thousands and eventually millions of qubits they're aiming for. What does that actually get us? The applications. People get most excited about cluster around a few areas. In medicine, quantum computers could eventually simulate molecular interactions with a level of precision classical computers simply can't reach, because molecules are themselves quantum systems, potentially shortening the path to new drugs and materials from years to months. In materials science, the same logic applies to designing things like better batteries, more efficient solar cells, or room temperature superconductors. In logistics and finance, quantum algorithms could, in theory, solve certain optimization problems, the kind involving enormous numbers of variables like global shipping routes or complex financial portfolios, far faster than any classical method. And then there's the one that makes cybersecurity experts lose sleep: cryptography. A lot of the encryption protecting your bank account, your messages, and basically the entire internet relies on math problems that are extremely hard for classical computers to solve, but that a sufficiently powerful, fault-tolerant quantum computer could theoretically break. This is exactly why governments and companies have been racing to roll out post-quantum encryption standards over the last couple of years. Not because Willow can break anything today, it absolutely cannot, but because the timeline for when a quantum computer could is no longer comfortably distant. To be clear, none of this is happening yet. Willow hasn't cured a disease or broken an encryption key. What it's done is provide the first solid hardware evidence that the foundational obstacle, errors getting worse as systems scale up, is not the immovable wall it looked like for 30 years. Segment 8. What happens next? Google isn't sitting still on this. In early 2026, the company opened what it's calling the Willow Early Access Program, inviting outside researchers to apply for hands-on time with the chip, still not available to the public, to run their own experiments. Applicants have to submit detailed executable proposals, with selections being made through the middle of 2026. It's a notable shift. Instead of only publishing results from inside Google's own walls, they're starting to let independent scientists kick the tires. The long-term roadmap Google has laid out is audacious. They're talking about scaling from Willow's roughly 100 qubits up toward a million qubit, fully fault-tolerant system. At the scale most experts believe, you'd actually need to run transformative, real-world algorithms. That is not a small jump. It's not even close to a small jump. But for the first time, there's a hardware result that makes the climb look like a long, hard engineering slog rather than a fundamentally unsolved scientific mystery. So is quantum computing solved? No. Is Willow a marketing stunt dressed up as science? Also no. What Willow actually represents is something rarer and, honestly, more interesting than either of those extremes. A 30-year-old theoretical promise that finally has hardware to back it up. For 3 decades, the entire field was operating on faith that quantum error correction would eventually work the way the math predicted. Willow is the first machine to actually show it in a lab with real qubits, on a real chip, checked by real peer review. That 10 septillion year number got the headlines. But the number that should actually stick with you is the simple one. Error rates, getting cut in half again and again every single time the system got bigger. That's the quiet, unglamorous data point that just rewrote what's considered possible. The race to a useful quantum computer isn't over. If anything, Willow just proved the finish line is real, that we're actually running toward it instead of chasing a mirage. The only question left is who gets there first, and what they do with it once they do.